right, so we're talking some more about graphs today, and we're going to start with kind of elaborating upon our notes from yesterday. So as we talked about yesterday and just now in the warm-up, graphical representations of data can tell us about the relationships between variables. But with some of our data, our ability to analyze and interpret the information we collect, we have to first linearize that data. So in order for us to make predictions or whatever else, we might need a linear graph in order to figure out or make conclusions or predictions from that data. From a linear graph, we can write an equation in that slope-intercept form to help us analyze or answer whatever questions we're trying to address. Several conclusions can be drawn by analyzing various aspects of a graph. We can learn about data in a graph by studying, and these are the different things I'm going to ask you to do whenever you look at a graph. I'm going to ask you to interpret what the slope means on that graph, and we just talked about that in the warm-up, and you've, I'm sure, been answering questions on that worksheet about the meaning of the slope. Later on, we're going to talk about what the area means underneath the line or curve on our graph. And then we're going to talk about the meaning of y-intercepts and x-intercepts on the graph. Depending on the graph we have, that may or may not hold meaning. And so I'm going to talk about each of these with you, so you can add notes underneath each of them. So let's start with slope. From a linear graph, we can write an equation in that slope-intercept form where y and x are the variables in our experiment, m is the slope of our line, and b is our y-intercept. And so if you're trying to find slope, you need to do so the same way that you've been doing in math class and hopefully been doing on that sheet that you're working on. Rise over run, or change in y over change in x. So you have to pick 2 points along your trend line and use those to find the slope of that line. And that slope will probably have some meaning. So let's look at this one. Okay, it says finding a slope on a scatter plot. So I have a scatter plot here that shows the number of visitors plotted against the average daily temperature for some beach somewhere. And it says draw a best fit line if the data appears linear. This largely appears linear, so I'd have a best fit line. Notice it does not connect my dots. It's not supposed to in this case. And some of them kind of touch the line, but you know, we're not really, most of them are not on my trend line. And it says to find the slope using any 2 points on the line of best fit. Okay, so I can use actual data points if they're on my line, but I don't have to. So for example, would I want to use that point that I just highlighted in green right here? Probably not, because it's not really on my line. It's kind of really close to the line, but it's not on the line. Okay, same thing with this point up here. In fact, if I used those 2 points, I would be finding the slope of that line, which is close, but not the same as my trend line. So it's important that you choose points on your line. If your trend line happens to go through the intersection of grid lines, use those. That's easy to read. Okay, and so here I have 2 points that I've highlighted that are actually on my line, even though they're not my data points, and those are the ones that I'm going to use to find the slope of my trend line. Again, rise over run, so change in y over change in x. So I have this point here, which is at x 92, y 525, and I have this point here, which is at x 82, y 75, and those are the values I plugged in here. Here's my y2 minus y1, x2 minus x1, rise over run, and I get a slope of 450 over 10. Now I know some of you left your slope like this the other day because I saw some of your papers. But I don't want you to leave it as a fraction. Okay, you might be doing that in math, I don't know, but in here we want to go ahead and divide that, and so we're not going to leave it as 450 over 10, we're going to write it as 45. And so the slope of that best fit line is 45 visitors per degree Fahrenheit. Any questions about that? This should be super easy stuff review from math. Okay, so again, don't leave it as a fraction. So that's the first thing, slope. Okay, and that slope will have a meaning depending on the graph we're looking at. The second thing that I may ask you to analyze in the graph is to find the area. Okay, sometimes the area under the line on a graph has meaning. this graph of velocity versus time, if I look at the area under the graph, it has meaning. Okay, I've highlighted the area. What do you think that area might represent? Some of you who took physics last year should know the answer to this, but those of you who haven't may not. Anybody know what the area might represent? Go ahead, Grayson, I know you know. Displacement. Okay, how far this object traveled. Okay, answer a question like this, or think about this question. If you drive 70 miles per hour for 1 hour, how far do you go? 70. You'll know that. That happens to be the area of that rectangle that I just highlighted in red. Okay, area is length times width for a rectangle. In this case, you use the numbers on your grid line. That's 70 and that's 1. 70 times 1 is 70. Okay, and so you can actually find that area under the graph. And for this one, I mean, it's easier to just answer the question than to look at the graph. But if all you have is a graph and it's not written out in words, you know, or maybe it's a more complicated scenario, you might need to find the area underneath your line on the graph. Okay, so what about this question? If you drive 70 miles per hour for 4 hours, now I'm looking at the whole graph, how far do you travel? Okay, well, you can probably do that one in your head too. Okay, how far would we travel? 280. And again, I'm finding the area. By the way, when I say finding area, it's always between the x-axis and the plotted line. Okay, so between my x-axis and wherever my line is. Sometimes my line is below the x-axis, and then I'm looking at the area in between that and the x-axis. But again, this is still length times width. 70 times 4, 280. Okay, so again, those might be easy enough to do, you know, without having to really look at the graph. But this one's a little trickier. Okay, take a look at this graph. It says, what about here? How far does this car travel in the first 2 hours? Okay, and so if I look at the first 2 hours here, I'm looking at this segment of my graph. Okay, you might be able to answer this question, except that I have an object that is changing its velocity, so it's not quite as easy for you to do in your head probably. But you can find the area, as long as you remember the formula for area of a triangle. Okay, what is the equation for area of a triangle? There you go. 1/2 base times height, or base times height divided by 2, whichever way you learned it. Same thing. Okay, so let's do that. Let's go ahead and call the base of my triangle 2 and the height of my triangle 60. 1/2, 2 times 60 is 60. And that means that in the first 2 hours, this car, if this represents a car, has traveled 60 miles. What we're doing here is we are taking the average velocity. Since they went from 0 to 60, the average is 30, and we are multiplying it by the time. But that's the same thing as finding the area of the triangle. Mathematically, it is exactly the same. Okay, so that's the first 2 hours. What if I asked you for the entire 4-hour trip? Okay, well, the first 2 hours we already have, so let's just find the rest of it. For the next 2 hours, you travel 60 miles per hour. Again, I can just do that with the area equation, or I'm sure you can do that very quickly in your head as just 2 times 60, which is 120 miles, meaning that they travel 60 miles in the first 2 hours and then 120 miles more. Their total is 180 miles in that 4-hour journey. Okay, so the area has meaning, and it will throughout this course, not just on velocity time graphs, but on other graphs that you see as well. If you're trying to find the area and you don't have a regular shape, break it into regular shapes. You'll notice I did this in 2 steps, the triangle and then the rectangle. Do that. Okay, if it's just a big rectangle, it's easy, or if it's just a single triangle, it's easy. But if you have a irregular shape, you're going to have to break it into normal shapes that you're able to find the area of. All right, so we've talked about slope, we've talked about area. Let's go ahead and talk about y-intercept. The y-intercept is the value of the dependent variable when x equals 0. So it's where it crosses my y-axis. It can show us when there is experimental error. And again, if you have data that is not linear, you need to linearize it first before you start interpreting this. Okay, or you may need to linearize it first. So if I take a look at this graph is plotting the mass of an object versus its weight in newtons. Okay, what would you expect my y-intercept to be? I would expect it to be 0, right? If I have no mass, should I have weight? No, I shouldn't. Okay, Okay, and so if you take a look at a graph like this, I can tell just looking at this that there is experimental error in my data somewhere. I don't know where with just this, but something happened where now it looks as if I have an object that has no mass but yet has weight, and that doesn't make sense. So I can tell that there's some error somewhere. Something I did was wrong when I collected my data. And your data isn't going to look perfect. Your data with those jumpies the other day, probably not a perfect line. Okay, if it is, you probably kind of fudged your data a little bit. I'm not expecting to see a perfect line. Okay, because it's real data, it's not going to be perfect. But you can tell if you have error if you have a situation like this. Okay, the y-intercept, what does this y-intercept tell us about the data? Well, it tells me that I have an error somewhere. Okay, so I kind of answered that second question. Could there be experimental error? Yes, something somewhere went wrong. Okay, this is the warm-up graph I had up there. It says, what do you think the y-intercept represents in this graph? What does this point represent? Birth, more than that. Give me another word. Birth what? Birth weight. Yeah, so y-intercept in this graph represents the birth weight of whatever baby this is, child this is. This child weighed 5 pounds at birth, according to this graph. Okay, does this show experimental error? Not necessarily. It's kind of hard to tell with just that, but that seems reasonable. Babies are born at 5 pounds. Okay, so there's nothing in there that tells me that it's way off or anything like that. Okay, so that's y-intercept. Now we're going to talk about x-intercept. Okay, I forgot to change this. The x-intercept is the value of the independent variable when y equals 0. It can also show us if we have experimental error. So this is the same data. If my graph looked like this, I'd have the same problem I did the first time. Because again, if I have 0 mass, I should have 0 weight and vice versa. Okay, so again, if you see something like this, it can show you if there's something wrong or if there was an error in your data collection. Maybe there's an error in your experimental design. Maybe there's a problem with your measuring tool. Maybe it's just a random error. Okay, and we're going to talk about types of error in just a minute. All right, here you go. Types of error in physics. Okay, so there are 2 types of error that you need to address in a physics class. Systematic error is error that is continually present, but you can correct it. Okay, so if you are using a balance to measure your jumpy and you forgot to zero it, okay, you're going to be off by that amount every time because it's a systematic error, but you can go back and fix that. Random error, on the other hand, is error that is present, but there's no predictable pattern to allow for correcting it. Okay, that's why we run multiple trials. When you were launching those things, you know, they're not exactly super scientific tools, so they go different heights each time. Okay, there's a little bit of random error in there just by virtue of the material that we were using in the experiment. Because there's not a way to make sure you press it down the exact same amount. There's no way of knowing if it's going to do the exact same thing. And so there was some random error, but that's why we run multiple trials to try to eliminate that error, because it's when you start averaging it together, you get rid of some of those outliers by bringing it in toward the middle, the more accurate value. Okay, so we address random error by running multiple trials to try to eliminate situations like that we can't really control. Okay, so systematic error, if you've got that in there, you need to fix it. But this we address with multiple trials. Okay, the next thing we need to talk about is accuracy versus precision. And I know you guys talk a lot about these terms. Well, I say that. I assume that you talked a lot about these terms in your chemistry class, or maybe you're in chemistry right now. But when we talk about accuracy, we're referring to how close a measurement is to its true or accepted value. Okay, you know, this bottle of water on my desk says that it is 500 milliliters. Okay, if I was to dump this, well, if it was full, it's not now, I opened it. But if I was to dump this out and measure it, and it's exactly 500 milliliters, then this is an accurate label. If I dump it out and I only have 490, I'm a little bit off on my accuracy, okay, or it may be overfilled. But your accuracy is how close you are to the accepted value, 500 milliliters. Okay, precision, on the other hand, if you're talking about the precision of a data set, okay, if I measure this 5 times, precision is how close my measurements are to each other. So if I run the same test 5 times, I take the same measurement 5 times, and I get 490, and and then I get 491, and then I get 489, my numbers are all clustered together, then I'm pretty precise. Okay, precision is how closely clustered your measurements are, how consistent they are. If you're talking about a set of data. Okay, how close your values are to each other. So thus, if you wanted to summarize this, accuracy is how right you are in your measurement, whereas precision is how consistent you are. It is possible to be precise without being accurate, or to have an accurate average, even if you weren't precise in your individual measurements. Okay, so it is possible to have one without the other, but obviously we are always aiming to have both. And sometimes that can be an issue, and I thought that was on this slide, it's on the next one, if you don't have the right tools. All right, so let's take a look at an example with some data. These students, it says acceleration due to gravity on Earth is 9.8 meters per second squared. 4 physics students conducted an experiment in which they measured the time it took a ball to fall from a height of 4.5 meters and calculated their acceleration. Their data is below. And so I have 4 students, Matteo, Nari, Flynn, and Imani, and they have collected this data and got these averages. So the first question is, who is most accurate? Okay, so taking a look at that data for just a second, Matteo, Nari, Flynn, or Imani, who is the most accurate? Nari, yeah, that's closest to the accepted value, which is up here in the question, 9.8, 9.82, that's really close. Okay, most precise. Who is most precise? I thought I heard somebody say it. Flynn. These measurements are very close to each other. He also used a more precise measuring device than Imani, for example, but he's only 2/100ths apart. So that's like the range of his data. He's only 2/100ths apart. So he would be the most precise. Okay, all right. Again, for accuracy, you can look at that average, or I could ask which particular measurement was most accurate, in which case I guess you would go with that one, but for just the whole set, looking at the average is what you'd want to do. All right, this is where I thought we were going before I went to that. But again, your ability to be accurate or precise sometimes also deals with the tool that you're using. Some of you, when you did your activity the other day with the jumpies, used the balances around the room on the counters, and if you did that, some of your data points are going to be really close together. Maybe you have multiple of them that are all on 7 grams because those balances are not precise. Measuring devices also have varying degrees of precision. Okay, you should always estimate one place beyond the smallest mark on a device. Now, of course, a digital scale, you can't do that, but if you're looking like at a meter stick or something, you can. This is very precise compared to this one here. Okay, because this one has a lot more markings. I can get a more precise reading. It's more precise because it has more markings or graduations on the device. I can estimate my height to the nearest 0.01 of an inch, if I'm using the inches side, or to the nearest 100th of a meter, because I can see, actually I can go past that. I can see the millimeters, so I can go one place past that. Okay, over here, this is what you see like on the door frame of a convenience store. They just have like whole feet and like each 6 inches marked, so it's not very precise at all. There's not very many markings. So it's not precise because there are a few markings, so your heights can only be estimated to the nearest whole inch. Okay, one place smaller than what you can see on that device. But again, you don't need that device to be precise. You're not, doing scientific experiments with it. You're just saying, you're looking at that in case somebody goes and robs the store, and then they can say, he was about 6'2", because you can see whenever they walk out the door in the security camera. In case y'all didn't figure out why those were there. But you can tell about how tall somebody is whenever they walk past it, assuming that it's, mounted correctly. All right, for the remainder of your class period today, you're going to be working on playlist 1, which is due tomorrow by 11:59 p.m. That means that you can be working on the assignment 104 if you haven't finished it yet. Obviously, the first page has the jumpies, but then after that, you are looking at other sets of data to try to graph those and answer questions about them. If you haven't done it yet, though, I'm going to encourage you to at least take a couple of minutes before you get into your work on that assignment 104 and take a look at 105. Let me go ahead and pull this up on the screen so we can talk about it for a moment, because most of you are going to be doing this in class tomorrow. And in order for you to be ready, you need to at least know what you're doing, because you really need to write an experimental design first. I'm going to zoom in a little bit. So I'm in our Schoology course. If I go into Unit 1, 1D Motion, if it decides to load, my computer's being really slow today. But it's inside of the Playlist 1 folder. It's the last thing that says checkpoint. And it may or may not load for me. Let me see if oh, there it goes. So Playlist 1, checkpoint. Here it is, 105 Experimental Interpretation. And so if I click this, it says, using a force sensor, 3 rods of different radii, and a ruler, determine what the relationship is between the maximum force required to break a rod and its radius. Then you're going to create and turn in a poster. Really, it's a sheet of paper. I had some people that did this like in Canva or on a slide. I don't care what format you choose. It can be handwritten, it can be digital, I don't care, because you turn it in here on Schoology. But here's what needs to be on that poster, okay? A brief description of your experimental design, which means you have to write an experimental design. Okay, a logical, organized listing of your data. Guys, what's a logical, organized way to list your data? Table. Awesome. Perfect. Okay, any and all graphs you use to determine the relationship. Since it told you that you're trying to find the relationship, we talked about 5 of those, so you should be graphing it to prove it and linearizing if necessary. And then an explanation. You're going to do claim evidence reasoning that explains the type of relationship between the radii and the breaking force. So all that's going to go on your poster or your infographic or whatever it is that you're turning in. You're going to turn in a picture of it, or if you did it digitally, you know, turn in the slide that you made or whatever. If you do share a link to something that's done digitally, please make sure that the link you're sharing takes me to something that is publicly viewable. Don't try to give me something that that I don't have permission to view. Make sure you share it with me first, or just attach the actual thing. Point being though, guys, you're not meant to do this alone. Ideally, you're going to be working in a group of 3 or about that size. So in order for you to do that and to have an experimental design and be ready to go tomorrow, you might want to take a minute to figure out who you're going to work with and talk to some people about how you might test this. I'm going to show you what the materials look like in just a second, and then maybe go back to 104 and work on that. Okay, if you have any questions for me, let me know. But again, 104 and 105 are both due tomorrow by 11:59 p.m.